Okay, in this presentation we are going to look at the moment generating function of a Poisson random variable. Okay, so there's one thing you have to remember about this really, and it's the Taylor series expansion. But let's just talk through it anyway. The moment generating function of a Poisson distribution with parameter lambda can be found using the definition of an MGF, moment generating function. So for a random variable x, it's the expected value of the exponential of t of times x. Okay, so it's essentially an expectation, an expected value, but of the exponential of t times x rather than the exponential, or rather than just x itself. Okay, the probability mass function of a Poisson random variable with parameter lambda is as follows: probability of x equal to k equals the exponential minus lambda times lambda to the power of k over k factorial for k equals 0, 1, 2, 3, etc., etc. Okay, so far it's straightforward enough. So just using the definition from the context of a discrete random variable, it is the summation of the value times the probability of the value. Okay, so we have the summation there from k equals 0 to infinity of the exponential of t times k times the probability of x equal to k. Okay, and so essentially what we're going to do there is put in our our probability mass function. So we have the summation of the exponential of t times k times the exponential minus lambda times lambda to the power of k over k factorial. So essentially what we can do there is take out that exponential of minus lambda term and take it outside the summation. And the rest of it is we have two terms that are in the power are written in terms of the power of k. We have the exponential of tk, and we have the lambda to the power of k. So you have two terms that are to the power of k. So what we can do there is combine them to a single term, lambda times the exponential of t to the power of k. So let's piece that all together. We have our moment generating function, mx of t is the exponential minus lambda times the summation from k equals 0 to infinity of lambda times the exponential of t to the power of k, collectively lambda and the exponential of t, divided by k factorial. Now, this is where we would use that Taylor series expansion. Okay, so the Taylor series expansion of the exponential of x, this is in the general form, around x equals 0 is given by the infinite sum. The exponential of x equals the summation from n equals 0 to infinity of x to the power of n divided by n factorial. Okay, the rest of it there is also interesting. So now this is just a general formula. This is not a sort of like in keeping with the notation we've used. This is just like let's say we're looking this up in a book. Okay, so going back to our question now, we have the moment generating function. So essentially what we're going to do there is notice that the summation term is the Taylor series expansion of the exponential of lambda times the exponential of t. Now this is probably a bit unusual that we have an exponential of an exponential. So the exponential term actually has its own exponential. Very unusual, you won't see this very often, but this is actually the case in this instance. So overall, the moment generating function is as follows. It is the exponential, after we employ the Taylor series expansion, it is the exponential of minus lambda times the exponential of lambda times the exponential of t. Okay? So therefore, the moment generating function is, we can simplify that expression there. We have mx of t equals the exponential of lambda times the exponential of t minus 1. And yeah, that's it. Again, very unusual to see an exponential term used as an exponential itself, but there you go. It's that case in this instance. And there we have it. That is the moment generating function of a Poisson random variable with parameter lambda. So we'll leave it there.